In the last lecture, we have seen how to find the analytic function if the real part is given or imaginary part is given or its linear combination, that is u plus v or u minus v is given. Okay. Now we are going to see the another concept, one more concept related to this analytic function. So first we need to understand what is going to be the harmonic function. So let us try to understand uh, the harmonic function. Okay. So here we'll try to understand what is harmonic function. So we can say that phi is equal to phi of xy be the function of that phi is equal to phi of xy be the function of x and y. Then phi is said to be harmonic function if it satisfies gamma square phi by gamma x square plus gamma square phi by gamma y square is equal to 0. So that is del square phi is equal to 0, where del square is equal to gamma square by gamma x square plus gamma square by gamma y square. Okay. So this del is the two-dimensional operator here. Okay, as we can see, the complex plane is the subspace of the three-dimensional space, and that's why this del operator we are considering in two-dimensional space. Okay, so actually the del operator what we have is in three-dimensional space is del is equal to I dabba by dabba x plus j dabba by dabba y plus k dabba by dabba z. This is the del operator in three dimensional. So if I consider del square, then del square is what? Del dot del. So it is going to be, we know the dot product. So dabba square by dabba x square plus dabba square by dabba y square and plus dabba square by dabba z square. Okay. So this is the del square operator in three dimension. We are in two dimensions, so we have to consider this in two dimensions. So complex plane is a two-dimensional plane. So where we have x and y, so we consider only in terms of x and y. Okay. Now this equation has a particular name. So that is phi, the function phi of xy is said to be harmonic function if it satisfies Laplace equation. So this equation del square phi or double square phi by double x square plus double square phi by double y square. Okay, this equation is called Laplace equation. Okay, so please be careful. Okay, because we have Laplace transform also, and we have the Laplace equation also. So this equation is called as Laplace equation. So if the function satisfies Laplace equation, then we say it is going to be the harmonic function. Okay, now how this harmonic function is related to the analytic function, because specifically we are all thinking of the analytic function, we are exploring the analytic function, but now how this term harmonic function pops in up, and then how it is related to the analytic function. So what we know is we know that the function f of z, if it is analytic, then we know about u and v, and now we have to add one more property to that. Okay, so what we can have is that f of z is equal to u plus iv be an analytic function. Okay, this is an analytic function. Okay, then we know this u and v satisfies your equation, but one more property we have to add now. Then this u and v are harmonic functions. Okay, so if f of z is an analytic function, then we know u and v satisfies your equation, and now we claim that this u and v are also harmonic functions. Okay, so these are going to be harmonic functions. So that is what you can say is double square u by double x square plus double square u by double y square is equal to 0, and double square v by double x square plus double square v by double y square is equal to 0. Okay, so when I know that the function f of z is an analytic function, then we can claim that u and v are harmonic functions, and hence if u and v are harmonic functions, they satisfy the Laplace equation. So u also satisfies Laplace equation, v also satisfies Laplace equation. Then moreover, okay, u and v are harmonic conjugates of each other. Okay, so that is u is harmonic conjugate of v, and v is harmonic conjugate of u. Okay, so we can say that this u and v are harmonic conjugate of each other. Okay, so now if I know u, I can find v. If I know v, I can find q. The link between this u and v is that the function is analytic. U plus iv is analytic. So if u and v are u plus iv is an analytic function, then we can have u and v are harmonic conjugate of each other, and hence we can find them each other. Okay, so we can find u and we can find v if I know one of this. Okay, but the link is that the function is analytic. F of z is analytic. Then only u and v are harmonic conjugates of each other. Otherwise, u may be harmonic, v may be harmonic, but they may not be the harmonic conjugate of each other if the function is not analytic. Okay, and that's why we have to be careful. Okay, so I hope you got the definition of analytic function and the harmonic conjugate. So, do you have any doubt in the definition of harmonic conjugate or harmonic function? Okay. So, basically, this harmonic functions and harmonic conjugate are related to the analytic function. Okay, and that's why if we know the function is analytic, then its real part and imaginary part are harmonic conjugate of each other. Okay, so let us see some examples based on the harmonic function only, and then we'll think of the conjugate. Okay, so we'll see some examples based on the harmonic function. Okay. So we go with the example. Show that the function u is equal to sin x cos hyperbolic y is harmonic. Okay, so we have to show that this is going to be an harmonic function. So we go with the solution. Okay, so what we have to do here, we have to show that this function is harmonic. So we have to show that it satisfies Laplace equation. So the function is harmonic if it satisfies this Laplace equation. So we have to find out the second order derivatives now. Okay, so up to it we have worked with the first order derivative. Now we have to go to the second order derivative, specifically second order partial derivative with respect to x and y. Okay, so now what we have to do is we have to find out the second order derivatives, and then we have to see that if their sum is going to be 0. So if their sum is going to be 0, then then we can say the Laplace equation is satisfied, and once the Laplace equation is satisfied, we can say that the function is harmonic. Okay, so let us see whether this function is harmonic or not. So what we can have is always write the given thing. So let we have is going to be sin x and cos hyperbolic y. Okay, be the function of x and y. So this is the function of x and y. So what we have to do is we have to find the second order derivative. So consider w by x is equal to. So what will be the derivative of this? It is going to be cos x into cos hyperbolic y. Okay, and again I differentiate this with respect to x. So I'll get w square u by x square. So it is going to be minus sin x, and you will be having here cos hyperbolic y. So this is going to be equation 1. Okay, so let this equation 1. Okay, and now differentiate this with respect to y. So w by y. So what you will be having here, sin x remains as it is, and the derivative of hyperbolic cos y. So it is going to be hyperbolic sin y. Again, I differentiate this with respect to y. So I'll be having w square u by y square, and this is equal to sin x, and this will be again cos hyperbolic y. So it is going to be equation 2. Okay, now I want to find the sum of these two second order derivatives. Okay, so let us find the sum of these two second order derivatives. So what we can say is adding equations 1 and 2. So we have what I am having here, double square u by double x square plus double square u by double y square is equal to, see the first equation, we have minus sine x cos hyperbolic y plus sine x and cos hyperbolic y. Okay, so what you can see, this is going to be 0 because this is a negative term, this is a positive term, and so the sum is going to be 0. So what we can say is we got double square u by double x square plus double square u by double y square is equal to 0. Okay, so we got this. What this is exactly? This is the Laplace equation. So we can say that is Laplace equation is satisfied. Okay. So once the Laplace equation is satisfied, then we can say the function u is harmonic, and hence we can say the function u is harmonic. Okay, so we can say the function u is harmonic function. Okay, so this is what we can have. Okay, now we'll try the another example. Do that. The function p is equal to e x square y minus y cube is harmonic. Okay, so we have to prove that this is going to be a harmonic function. Okay, so we can have let p is equal to e x square y minus y cube be the function of x and y. Okay, so this is going to be a function of x and y. Now what we have to do is we have to find the second order derivatives. So first we'll have double b by double x. So find the derivative of this with respect to x. So it will be 6xy. And then I'll be having double square b by double x square. So it is going to be 6y. So let this equation 1. And now we have, okay, so what we'll be having, we have to find the derivative with respect to y now. So double v by double y is equal to ex square minus 3y square. And then find the derivative with respect to y again. So double square v by double y square is equal to, the derivative of this term is going to be 0. The derivative of this term is going to be minus 6y. So this is going to be equation 2. Now, if I want to find whether it is harmonic or not, I have to take the sum of these two second order derivatives. So what we can do is we can have the sum of this. So adding equations 1 and 2, we get. So what we'll have here, so it is double square b by double x square plus double square v by double y square. So it is going to be 6y minus 6y, it is going to be 0. And hence what we proved actually, we proved that double square v by double x square plus double square v by double y square is equal to 0. So what we got here? We got the Laplace equation is satisfied. So that is, we can say the Laplace equation is satisfied. Okay. So the Laplace equation is satisfied. And as we know, if the Laplace equation is satisfied, then we can say the function is harmonic. So function E is harmonic function. Okay, so the function V is a harmonic function. So is there any doubt in this two examples that we have proved the function is to be harmonic? Okay, that's great. You don't have any doubt in this two examples. Good. Okay, so we'll try another example. Okay. So now let's have another example. Do that A is equal to e raised to x cos y plus sin y is a harmonic function. Is a harmonic function. So we can go with the solution. So what we'll be having here, let E is equal to e raised to x cos y plus sin y be the function of x and y. Okay. And so we consider the derivative of this x, derivative of this v with respect to x and with respect to y, and then we'll find the second order derivative. So what we'll be having here, dou v by dou x. So we know we have this is only the function of x. So we have the derivative of e raised to x is as it is. So it is going to be cos y plus sin y, and then again the derivative of this first order derivative with respect to x. So we again have the derivative of e raised to x is e raised to x only. So it is cos y plus sin y. That is equation 1. Okay. Now we have to find the derivative with respect to y. So what do we have here? Now consider dou v by dou y is equal to e raised to x. Derivative of this cos y is going to be minus sin y plus the derivative of sin y is cos y. Again find the derivative of this with respect to y. Okay, so we have e raised to x remains as it is minus the derivative of sin is going to be cos y and the derivative of cos y is minus sin y. So let this equation 2. Okay, now we have the both second order derivatives. So what we can do is we can add this 2 and hence we can write adding equations. Yeah.
Sir, so first derivative is
Yes.
so first derivative will be different.
Which first
Minus
derivative?
cos y will
The
be
dou v by dou x or dou v by dou y?
dou square v by dou x square y.
Okay. How it will be different? We are differentiating with respect to x, no? So the derivative of e raised to x is e raised to x. So what we know is the d by dx of e raised to x remains e raised to x. Okay, so here what we
Okay,
have,
yes, yes, I got it.
yes, this is the function of x only. This is the function of y only. So it will be treated as a constant. So this remains as it is, and this only we have to take the derivative, and the derivative remains as it is. You got it?
Yes, sir.
Yeah, that's good. Okay, okay. So now we add the equation 1 and 2. Okay, so if we add the equation 1 and 2, what will get here? So we get that double square v by double x square plus double square v by double y square is equal to. See the first term. What we have? E raised to x cos y plus sin y plus e raised to x minus cos y minus sin y. Okay, and hence what we can have this. So e raised to x is being a common term, we can have it outside, and we can write this as cos y plus sin y minus cos y minus sin y. So you can see this cosine will get cancelled, this sine will get cancelled, and you will be having this is the term e raised to x into 0. So this will be 0. So what we got actually, we got double square v by double x square plus double square v by double y square is equal to 0. So we got this. So what this is exactly? This is the Laplace equation. Okay. So what we can say is that is Laplace equation is satisfied. Okay. So when we have the Laplace equation satisfied, we can say the function A is a harmonic function. Okay. So we can have V is going to be the harmonic. Okay. So now do you have any doubt in this example? Is there any doubt in this example? Yeah. Prathamesh, what is the doubt? You may ask, please. Prathamesh Gaikwad, you have any doubt? Uh, it is daba v by daba y. Okay, not d. So d means the total derivative. Here we are having the partial derivative. Okay. So what we have here, see, you have doubt in this derivative. Okay. So what is the function we have? See, this is v e raised to x into cos y plus sin y. We are finding the derivative of this with respect to y now. You have doubt here. So that is dabba v by dabba y. So when we are in partial derivatives, we treat the function of the remaining variable as a constant. So here we are finding the derivative with respect to y. So x will be treated as a constant. If I treat this x as a constant, so what it remains? It remains this is the function of y. So we have to find the derivative of this term only, and what we have d by dy of cos y is equal to minus sin y, and d by dy of sin y is equal to cos y. Okay. So here I have taken the derivative of this term with respect to y. So which is sin y here minus sin y, and the derivative of sin y is cos y. Okay. So according to this derivatives that we have studied earlier. Okay. So, is your doubt clear, Prathamesh? Prathamesh, is your doubt clear now?
No, sir, no doubts.
Is your doubt clear, Prathamesh? Okay, that's good. Okay. So, that's good. Okay. Now, next we have okay. So now we have the idea of the harmonic function. Okay. So if you have the idea of harmonic function, then the next question is how to find the conjugate. Okay. So we have to consider harmonic conjugate. So now we know if the function f of z is analytic, then u and v are the harmonic conjugates of each other. So the question is, if I know u or v, how I am able to find the harmonic conjugate now? Okay, so what we'll be having here, find harmonic conjugate, we consider the following steps. Okay, so what are the steps we have? First, okay, so let u or v be the given function. Okay, this is u or v. So you should not be confused. U or v. Okay, so anything out of these two, and we have to find out the other. Okay, so this will be the given function. Okay, then what we do is second step is find the analytic function. F of z is equal to u plus iv using Milne-Thompson method. Okay, and the third, replace z by x plus iy and separate the real and imaginary part. Okay, so we have to separate the real and imaginary part. So if I want to find out if u is given, then I have to find out what is v. If v is given, then I have to find out what is u. And this way you are able to get the harmonic conjugate of any function. So this harmonic conjugate has to go through the analytic function, because when it will be real or imaginary part of the analytic function, then only we are able to claim that the other function is a harmonic conjugate. Okay, so without finding or without knowing the function to be analytic, we cannot claim that we got the harmonic conjugate, and that's why we have to be careful. So one more important thing that I want to tell you. Okay, so do not abbreviate this term, Milne-Thompson method. Okay, so why this I'm telling you repeatedly, because Milne-Thompson method and you abbreviate it as MT. So MT is a standard abbreviation of Milne transform. Okay, so there is another term in mathematics called Milne transform, and so MT is a standard abbreviation for Milne transform. As LT is a standard abbreviation for Laplace transform, so MT is a standard abbreviation for Milne transform. And the most important thing that Milne transform is not related to complex anyway. So we should not abbreviate this. We should always write this as Milne-Thompson method. Okay, do not abbreviate this. Okay, so these are the three steps that we have to follow to find the harmonic conjugate of the given function. Okay, so let us try to find the harmonic conjugate. Okay, so we'll try an example so it will be more clear. So what we can have is show that q is equal to x cube minus 3xy square is harmonic function. Hence, find its corresponding analytic function and harmonic conjugate. So now in this example, we have to show that it is harmonic function. We have to find its corresponding analytic function, and also we have to find its harmonic conjugate. So here what we have to do is we have to show that U satisfies the Laplace equation. Moreover, we have to use the Milne-Thompson method to find analytic function. And as I have given you, to find the harmonic conjugate, we have to replace z in f of z by x plus iy and separate the real and imaginary part so that we are able to get the harmonic conjugate. So these are the steps that we have to follow. So let us write the answer step by step. So we go with the solution. What is, if I want to find out the analytic function, what is the first step I should have? So let f of z is equal to u plus iv. As we know, we have to use the Milne-Thompson method. Be an analytic function, okay, with real part u is equal to x cube minus 3xy square. So without loss of generative, we consider u as a real part and v as a imaginary part. So this is going to be a real part of this analytic function. So we have to find out the analytic function as well as we have to find out this v also. Okay, so what to do with the to find the analytic function? So consider the first order derivative. So phi 1 of xy is equal to w by w x is equal to, so we'll be having 3x square minus 3y square. Let this equation 1. And we have now we have to show that this is going to be the harmonic function also. So we have to find the second order derivative of this also, and hence as we have calculated the first order derivative, we'll calculate the second order derivative. So w square u by w x square is equal to, what you'll be having here, it is going to be 6x. Okay, so this will be 6x equation 2. And now we have the derivative with respect to y. So phi 2 of xy is equal to, so let us find the derivative with respect to y. So that will be w by wy. So the derivative of this time is going to be 0 because we don't have any y here. And here I'll be having minus 6xy is equation 3. Now I need the second order derivative of this with respect to y. So I have w square u by w y square, and this is going to be minus 6x. So let it equation 4. Okay, so I want to show that this function is harmonic, so I have to add equation 2 and 4. So we can say adding equations 2 and 4 we have. Okay, so what we'll get here, see carefully that double square u by double x square plus double square u by double y square, and this is equal to 6x minus 6x is equal to 0. So we got here double square u by double x square plus double square u by double y square is equal to 0. Okay, so what we can say is that is Laplace equation is satisfied. Okay, so Laplace equation is satisfied. Then what we can say is uh, we can say u is a harmonic function. So we can say u is going to be an harmonic function. So once I know that u is going to be harmonic function, so first part of this problem we have solved. So we wanted to prove that this is going to be a harmonic function. We proved it, and now we have to find the corresponding analytic function and harmonic conjugate. So if you see two steps of the Milne-Thompson method already we have completed. The first step to write the function to be analytic with the given part. The second step finding the first order derivative. And now the third step of the Milne-Thompson method is to put x is equal to z and y is equal to 0. Okay, so what we can do is we put x is equal to z and y is equal to 0 in equations 1 and 3 we get. So what we are able to get is, see, in equation 1 we have to put x is equal to z. So this will be 3z square, and this will be 0 because we are putting y is equal to 0. So we got here that phi 1 of z0 is equal to bz square, and phi 2 of z0 is equal to 0. And hence what we can say is the fourth and final step of Milne-Thompson method. So by Milne-Thompson method, the analytic function f of z, okay, is given as. So what is the analytic function you will be having? F of z is equal to integration of phi 1 of z0 dz minus I integration phi 2 of z0 dz and plus c. So where this c is going to be the constant of integration. So where c is constant of integration. Okay. So where c is going to be the constant of integration. Now put up these values. Okay. So what we can do is we put up these values, and hence we have f of z is equal to integration 3z square dz minus I integral 0 dz plus c1. So this is 3z cube by 3 and plus c. So we can have z cube plus c. So we got here f of z is equal to z cube plus c. So this is the required analytic function. So this is going to be the required analytic function, and now we have to find the harmonic conjugate. Okay, so what we do is replace this z by x plus iy and find the real and imaginary part. Okay, so we can do here as put z is equal to x plus iy in above equation we get. So what we are able to get here, see, f of z is equal to x plus iy bracket cube plus c. Since I know that a plus b bracket cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Okay, so simplify this, x cube plus 3 x square iy plus 3 x iy square plus iy cube and plus c. Okay, so what we can have here as this is equal to x cube plus 3i x square y. Then this is dx, I square is minus 1 y square, and this is minus I y cube. Why this? Since I square is equal to minus 1, I cube is equal to minus I, and then this plus c. So we can have x cube minus 3xy square plus I 3x square y minus y cube plus c. So this is f of z. Okay. And now we have to separate the real and imaginary part. So this is going to be the real part. This is going to be the imaginary part. Hence we can write. So separating the real and imaginary parts, the harmonic conjugate of u is given as, okay, b is equal to, so it is going to be b x square y minus y. Okay, so the question is how we will be sure that this is the correct answer. Okay, so what you have to do is you have to always compare with the given thing. So what was given to you? The given is u. Okay, so what is the u given? X cube minus 3x square. So that was a real part. Whether you are able to get the real part properly. So if you are able to get the real part properly, that means this answer is correct. Okay, so if you are not able to get the given part properly, that means the whatever you have calculated is not correct. Okay, so that's why we have to check whether the given part we have obtained correctly or not. So here we have obtained the real part correctly, and hence our imaginary part is also correct. Okay, so this way we are able to calculate the harmonic conjugate of the given harmonic function. So the function has to be harmonic, then it has to be the real or imaginary part of the analytic function. And once it is real or imaginary part of the analytic function, then only we can get the harmonic conjugate. And that's why we have to go through the Milne-Thompson method, because it guarantees to get the analytic function. Okay, so that's what we have. Okay. So do you have any doubt in this example? That's great. Okay, good. Okay. So that's good. You understood this harmonic function and calculating the conjugate.